Hello everybody, welcome to this notebook about object detection. Now we have learned about image classification and we have learned about semantic segmentation. And just to refresh your memory, in image classification, the input is an image and the output is one class label. So we use a single word to describe the entire image. On the other hand, semantic segmentation takes it to the next level. For every pixel, we have a class label, right? So you can see that in semantic segmentation, there is a lot more information we get for every class. There could be multiple classes in the same image. There could be cats and dogs. And for every cat and dog, you find for every pixel, we have a class label. So you can find all the pixels that belong to the cat class. You can find all the pixels that belong to the dog class, and so on and so forth. But sometimes image segmentation, it has so much information that it is an overkill. And because it's producing so much information, it's analyzing the image so deeply, the processing power it needs is also very high. Sometimes we need a compromise between the two. We want something that is fast, but maybe not as detailed. We don't need as much detail as we have in semantic segmentation. So object detection is a sweet compromise in the middle. In object detection, the input is an image and the output is a collection of bounding boxes. And for every bounding box, we have a class label. So let me show you an example so that it's clear to you. For example, here, this is the output of an object detector, which has two classes, car and person. So you can see that we have a collection of bounding boxes. For every bounding box, we have a class label: car, bicycle. Actually, there are three classes: car, person, bicycle, etc. Right? And in a lot of applications, we don't need to know the detailed segmentation of the car. If you give us a bounding box, that is sufficient. Let's say you want to count cars, that's sufficient. Let's say you want to avoid cars. Even for that application, if you have a bounding box around the car, that is sufficient. All right. So object detection is a very powerful technique, because it combines, it's a sweet compromise between image classification and image segmentation. All right, so let's learn about a little bit about the history of object detection. We will first learn about something called a two-stage object detector. Initially, when I would say before, let's say in the first decade of the 2000s, like between 2000, the year 2000 and let's say 2005, 2010, people used to create a single class object detector. So you would have a face detector, you would have a person detector, and these would be separate models, right? And the reason is that the algorithms were not sufficiently developed, right? And it used to be very expensive. In fact, we used to take a classifier. So imagine that the classification you have already learned about. You take the classifier and then apply it to every pixel in the image at different scales. So if you want to create a face detector, you would basically create a face classifier first, which could tell the difference between a face and not a face, right? So it can tell the difference, that is your classifier. Then you take different patches inside the image, and for every pixel, you basically have a sliding window. You create a window inside the image, which is a small crop of the image. Then you slide it one after the other, and you do that for every pixel. Now imagine you're going to detect the face at many different scales. So you have to create that patch for every scale. And then you have to actually evaluate this classifier at every pixel. And even if you decide to skip a few pixels, even then that's a lot, right? You're evaluating the image classifier at, let's say, thousands of locations. Right? And that is why the sliding window approach was very expensive. So next came this idea of region proposals. So region proposal was the idea that, okay, you will learn from the image what is a region, what could be a potential object, right? We don't know for sure whether that object is real or not, but what can be a potential object? So a region proposal algorithm would output from the image, it would output a collection of bounding boxes. We still do not know what the classes for these bounding boxes would be, but it would create a collection of bounding boxes, and then you could evaluate these bounding boxes and say whether that that actually contained an image or not, contained a class or not. For example, here you could see this idea of regions. It basically extracted different regions, and then you used every region, you evaluated every region and checked whether there is a particular class in that or not. So this was the idea of RCNN. This, at that time, it was a very impressive algorithm. What they did was they took a region proposal algorithm called selective search, and they basically ran selective search on the image, got a lot of bounding boxes, and then these bounding boxes they ran through a convolutional neural network and got a lot of features, right? So these feature vectors they could run through a classifier called support vector machines. So these are the kinds of things that we learn in our detailed course, Deep Learning with Pytorch, which is a paid course. But I'll explain in a little hand wavy way. So basically these convolutional layers were used to create feature vectors, which went to an image, a learning algorithm like support vector machine, which was able to classify these feature vectors. If you don't understand all the details, it's fine, right? The main thing to keep in mind is that this RCNN was still very expensive, right? Because it was much faster than the sliding window approach, because it created, instead of tens of thousands of pixel locations, now you had to do the evaluation only at, let's say 2000 locations, right? So it was much faster, but it still took about 40-50 seconds for a single image to detect all the objects in the image, right? The accuracy was reasonable, but not, at that time it was state of the art, but the speed was just, still not useful. Then came fast RCNN. So in fast RCNN, the region proposals were still done using selective search. They still found bounding boxes using selective search, but they removed this external classifier called the SVM, support vector machine. Instead of using support vector machines, they used convolutional neural networks, which was the in thing at that time. So even in RCNN, they had used convolutional neural networks, but they had not used it in the most efficient way. Now, using it in the right way, fast RCNN was able to remove the last part, which was called support vector machine, and do the classification task using convolutional neural networks. Okay, so that gave, it was slightly faster, and it was, I think, it still took about 2 to 3 seconds. But imagine, right, in less than a year, you're going from 40-50 seconds to 2 seconds. So this was like, we were very happy about fast RCNN. Then came faster RCNN. Now, faster RCNN did the right things. The region proposals that were being generated initially, right, in RCNN as well as fast RCNN, they were based on this algorithm called selective search. There were two problems with selective search. Selective search was not a learning algorithm, which means that it did not actually learn from the data. It was an algorithm somebody put together based on, they had some heuristics about how to use the color, texture, etc. to define what an object is. But the right way to do it, the right way to solve some of these problems is to learn what an object should be from the data itself, right? And that is something selective search did not do. And selective search was also very, very expensive. Now, using convolutional neural networks, because convolutional neural networks is already extracting those features. It's extracting the features. It kind of understands what's in the image, right? At a low level, at a high level, at all levels. So convolutional neural networks, all these features were already present. We are already calculating those. Why not use the same features for doing both things, right? For finding the region proposals as well as for doing the classification. So you find the bounding box as well as do the classification using the same features. Now, this looks obvious right now, but at that time, this was, blazingly fast. We could do, object detection in say about 200 milliseconds or so, right? So this is approaching real time, not quite there, but the quality was very good. The quality of faster RCNN was very good. And that is why for the longest time, people were comparing the results to faster RCNN, and all the focus was on improving the speed while maintaining the quality of faster RCNN. And these algorithms that I just described, these three networks, RCNN, fast RCNN, and faster RCNN, they also belong to a class of techniques called two-stage object detection. Because here, you're doing the detection in two stages. First, you're finding the bounding boxes, and then you're doing the classification to say that, okay, these are the bounding boxes, these are the classes for the bounding boxes, right? And because of these two stages, it was the process is still expensive. Later in this mini course, we are going to discuss YOLO, which is you only look once. As the name suggests, it's not you only live once, which which is a play, right? They have made a play on that expression. You only look once. In you only look once, YOLO, it is blazingly fast, right? Initially, the first few versions of YOLO were not as accurate as faster RCNN, but it was blazingly fast, right? It was like you could get 20 to 30 frames a second, even in YOLO V1. So there, the main contribution was that it was a single shot detector, which means that you did not have to go over the image in two steps. You could do the prediction in one step. We will go over YOLO later in the course, but let's use faster RCNN, which is part of Pytorch. So just to give you a comparison, right? We have these various metrics along which we have put this table. So RCNN released in 2014. It uses selective search, and after that it did CNN processing, and this was very slow, 40 to 50 seconds per image. The accuracy was good. At that time, it was considered very good. And it was not end-to-end trainable. As I had mentioned, that selective search was not was a separate algorithm. And then they basically pieced together the best algorithms of that time and put together this pipeline, right? But it was not end-to-end trainable, which means that every piece you had to train it separately, and some of it was not even trainable. Here, fast RCNN, it was sort of end-to-end trainable, but the selective search part, which was used for region proposal or generating those bounding boxes, that did not involve any training at all. So that was a drawback. And finally, we got faster RCNN, which had all the good elements, but it was still about taking about 200 milliseconds. So not the at that time, actually, to be honest, at that time it felt like it was very fast until YOLO came along and other single stage object detectors came along. All right, so how do we use faster RCNN in Pytorch? Fortunately, they have a pre-trained model. And as I had mentioned that you need, we are going to use faster RCNN with a ResNet 50 backbone. And this is very common. ResNet 50 is probably the most popular feature extractor that people use in deep learning. So for every image, for every image as input, this is the output you get. You get, the input is, first of all, as we said, that we have to send the image as a batch. So the number of images, you could send multiple images at the same time. And C is the number of channels. This is usually an RGB image. For faster RCNN, it is an RGB image. H is the height of the image and W is the width of the image, right? That's what we are going to pass as input. And the model is going to return bounding boxes, right? Which is X0, Y0 and X1, Y1. 2 points, the top left corner and the bottom right corner of the bounding box. That's what it is going to return. And so it it will have 4 elements, and it will also have a class label, right? So let's, and finally, it will have a score that this, the prediction score, that how much we trust this prediction. So you can threshold the score prediction and get only the higher quality objects. Sometimes you may have to use a lower threshold. Let's say you're using a night scene, right? And it's very important to get the objects. It's very important to get the car or the person in the image, even though it may generate some false positives, right? In that case, you lower the threshold. For example, in high security applications, sometimes it's necessary to lower the threshold because you cannot afford to have a false negative, right? You need to catch all the people in a restricted area, even though sometimes it will give false alarms. That's okay, right? So for those kinds of applications, you lower the threshold. For applications where it's very important to get the right results only, then you can increase the threshold. Okay, so let's look at the code. As always, we are importing some standard libraries. We are importing PIL, Matplotlib, Torch Vision, transforms from Torch Vision, etc. also, and so on and so forth. Here we are setting the random seed for NumPy. The reason for setting the random seed, to a particular value is that we want to get consistent results, right? Sometimes if you don't set these seeds and you're using a random number generator, you will see different results in different runs. But here we are using a random number generator to select the color of bounding boxes, and we want to make sure that the colors don't keep changing on us. Okay, next we basically get the faster RCNN with ResNet 50 backbone as our model. And as you can see, the weights are also present, right? These weights are also provided by Torch Vision itself. So it's very convenient. They have provided the architecture and the weights. All we have to do is run the model and it will give us the right results. As always, we are going to put the model in evaluation mode as opposed to training mode. Whenever we want to do inference, whenever we want to use the model for evaluation, for inference, for running it, then we have to put the model in eval mode. If you don't do that, it carries a lot of baggage from training, and it is going to do a lot of calculations which are not necessary, and things will be much slower. Okay. Next, we define the categories, right, that we are interested in. This model was trained on the COCO dataset, so it has all the object categories that COCO has. Now, COCO is the short form for, or MS COCO is basically Microsoft helped in creating this dataset. So MS COCO stands for Microsoft Common Objects in Context, right? So this is a very popular dataset. It has about 80 different classes. The original COCO paper had 91 classes, but when they released the dataset, it had 80 classes. So, and you can see the entire list. We have included a link here where you will learn more about the COCO dataset. But here's the list for us. 0 is background, 1 is person, 2 is bicycle, 3 is car, and so on and so forth. All right. Now we are going to describe the colors. What we have done is we are randomly sampling some colors to represent these classes, right? So person 1, we are just using random numbers, 3 random numbers, RGB, right, to figure out. So if you use a different seed here, you will get different colored bounding boxes in these cases, right? So that's all it's doing. Okay, so once we have done that, we basically run this block. And when you run this block, obviously this particular model may not be present on your Colab instance. And so it's going to download that instance and everything will be set for you. All right, now let's look at this function getPrediction. This basically takes an image path and a threshold, and the threshold is on the confidence score. We want to select only the boxes where we are confident that the object is there, right? So anything above the threshold will be selected, anything below the threshold will be rejected. So we first read in the image and then we create a transform. Now, previously we had seen that most of the time in the transform, we resize the image, we do a center crop, etc. But here we are doing none of it. The reason is that this network automatically resizes the shorter side of the image to 800 pixels, and the longer size is whatever it is, right? So you don't need to resize. It can take any sized image, and at the same time, it's not working on a fixed size image. So that's great. Now we apply. The only thing we need to do here is to convert it to a tensor, right? A Pytorch tensor, and that's all the transformation that is needed. Okay. So we do that, and then we perform prediction on using the model. And as you know, that when we want to perform a prediction, all we need to do is pass in the image, and it is going to do the prediction. Once we do the prediction, we get, the first element of that structure is the prediction data that we are interested in. And as always, we are going to detach the computational graph. So we are going to use basically detach, move it to CPU, and then convert it to a NumPy array. So we do that for labels, boxes, and scores. So this prediction data contains three things: labels, which is the class label like cat, dog, etc. Boxes, so it contains an array of boxes and an array of labels corresponding to those bounding boxes. So the bounding boxes are basically, the box inside which the object is contained. And the scores. The score is the confidence we have that there is actually an object, right? So if you want to get a lot of boxes, then you use a lower confidence score. If you want to be very strict, then you use a higher threshold value. And that's what we are doing in the next line. You can see here, we do valid indices. We find all the scores for which it is greater than threshold. And once we have done that, we can essentially get all the bounding boxes in pred boxes and all the classes in pred underscore class for the scores the scores are greater than the threshold. So we are only looking at valid indices and collecting all those boxes and all those classes into these structures. And then we are letting it, returning that prediction boxes as well as the classes. Next, we have another function, the object detection API. This is the high level function we are going to use. It takes in the image path and the threshold value. And here we are going to do all the drawing as well, not just do the prediction, but also draw the results on the image. All right. So let's see. First, we get the predictions, we get the boxes as well as the prediction classes. And then we read in the image inside this. We convert it to RGB format. Sometimes when you use OpenCV to read in the image, you will notice that the colors are flipped. In that case, you probably forgot to convert it to RGB values. So you can use the CVT color to convert the image to RGB from its original BGR format. Next, we find the thickness of the rectangle, which we are going to use to draw the rectangle. And this is basically based on the size of the image. If the size of the image is large, we can use a thicker rectangle and so on and so forth. Assuming that, usually bigger image means the objects would also be bigger. And then we also calculate the thickness of the text we are going to use to render. And we are basically using something that is related to the thickness of the rectangle. Next, we go over all the boxes. So we got an array of boxes which contains all the boxes, and then we also have the labels corresponding to it. So first, we go over all the boxes. We get the 2 points, which are the top left corner and the bottom right corner of every box. We get that. We get the color corresponding to that class, right? So basically we pass in the prediction class and we get the color corresponding to that prediction class. And then we draw a rectangle, right? This is the image, and cv2.rectangle is basically OpenCV's method for drawing a rectangle on an image. So we pass in the image, we pass in the 2 points, the top left and the bottom right corner. We pass in the color and the thickness of the rectangle we want to draw. So now we have drawn the rectangle, but we are also going to draw a text box on top of the rectangle if there is space, or inside the rectangle if there is not much space. So to do that, first of all, we need to find the rectangular space occupied by the text so that we can first draw the box. So let me just show you here. We have already drawn this big rectangle, right? The bounding box for the person. Now we are going to draw this rectangle and then write person inside it. So that is why we are finding the rectangular extent of this class, and we are going to fill in that rectangle and then write the class name inside it. Okay, so that is what is happening here. Right here, so we are calculating the width and height of the text box. For example, the person class, we are finding it based on the thickness and that we have selected. Okay, so once we have the width and height, based on that, we are calculating whether, if there is enough space, we want to draw this rectangle outside the bounding box. If there is not enough space, then we will draw it inside the bounding box. That's what this calculation is doing. And once we are done with that, we basically draw a rectangle which is filled with the color, right? And inside that, we are writing the text with white color, right? So the person class, you can see this rectangle is the same color as the class, the color we associated with that class, and that inside that we are using a white color to do that. Okay, so that's all that is happening. You can look up, the syntax of put text. You can look up the syntax of cv2.rectangle. These are methods inside OpenCV that allow you to basically draw rectangles and draw text on image. So that's all that is happening. And then finally, we create a figure and show the image. All right. So that function is very simple. It basically takes, this object detection API, it takes an image, path, and a threshold, and then it calls the get prediction method that we have, a function that we have defined. We get the boxes and the prediction classes, and then we simply draw the boxes and the prediction classes on the image. That's all it is doing. All right, so next we have a utility function that allows you to download a file using wget. So, it's pretty straightforward. I'm not going to go over it. We have already covered this in previous notebooks. And then we have a directory called inference_dir, and all the images, etc., get stored inside this inference directory. Next, we are going to download this file and call it people.jpg. We are going to pass it to the object detection API function that we created, and we are going to pass in the file name as well as the threshold. Here we have chosen a threshold of 0.8. If some people were not detected, we could have lowered the threshold to detect more people. But in this case, this is a very well-lit image and everything looks really good. So, a high threshold will work. Sometimes when we are working with noisy images, etc., if there are, certain occlusions, etc., in those cases, we may need to reduce the threshold. Okay. Now, here we are downloading the vehicle image, and then we, again, call the object detection API and run this image through it. You can see that it detects vehicles or cars. We have some people are detected, all the people are detected, also the bicycles are detected, right? So again, there are 80 different classes. So anything in that class would be detected. Anything in the image which corresponds to one of these classes, they would be detected. All right. So let's keep going. We again download another image, traffic_scene.jpg. And this is a funny one because you can see, obviously, we have detected all the cars. Also, one of the trucks, the truck is also detected. And right here, there's a person inside the car that also gets detected, which is really funny because you can barely see the person. In low light conditions, you can see that it does reasonably well. We downloaded nighttime.jpg and it sort of detects, okay, there is bicycle, there's a person, car. If you play with these enough, you will notice that, it's not 100% accurate. It will miss certain cars. It would sometimes call a car a truck. So such things can happen, and that's very common. And you may also find, if you experiment with your own image, you may find situations where it does not, it misclassifies certain boxes. It could not detect some boxes. You should play with the threshold and see what happens. If you lower the threshold to 0.5 or even lower, you will start seeing false positives, a lot of false positives, right? So play with it and you will get a sense of what the failure modes are. Again, we download another image called crowd.jpg, and you can see that a lot of detected. So does a pretty reasonable job for some of the classes. You can also see that there is a handbag class which gets detected here. You see a handbag here, and this is a handbag that is also detected. Next, let's go over some code to see the inference time both in the CPU as well as the GPU. So here we import the time package, we load the model again. This time it is a ResNet 50, faster RCNN ResNet 50. And then we also load the default weights. We set the model to the default, evaluation mode. Now for check inference time, this is the main function that basically takes an image path, which means the entire directory. And then inside the entire directory, whatever images we find, we are going to do inference on it and then take the average of all the images in that directory and report the number. So again, here we have, the image path. So this one takes just one image. Sorry, I misspoke previously. It takes just one image and it gives you the inference time for that image. And then there's subsequent code coming later on where we go over in a loop over all the images in the directory and give the average. So this one takes in just the image name. We load the image, we do the transform. This we have already gone over. We transform the image and then we set the model. We send the model to CUDA, which means that we send it to the GPU. We send the image to the GPU. If that is not the case, we send the model to CPU. And this is just to confirm that it is actually going to the CPU. By default, it may or may not go to the CPU. So, and then we have image equals image.cpu. All these tensors, we are passing it to the CPU. We have seen this before while working with tensors in Pytorch. We can tell it to go to the CPU or go to the GPU, depending on this, by using this method, CPU versus CUDA. Okay. So now the image is in the right, device, either the CPU or the GPU. And then we basically measure the start time. We call the prediction function, and then we find the end time, and then return the time it takes, end time minus start time. All right. So to do it over multiple images, we basically create image paths, right? This is basically we look at all the images in the inference directory, all the ones that we downloaded, 4 or 5 of them, and then we basically check. We sum up all the inference times. Here you can see that we loaded everything in our GPU, right? And we loop over them, and then we sum all the GPU times, we sum all the CPU times for all the inferences over all these images, and then we report the average, right? We basically say how much time it took for the CPU as well as the GPU. Okay. Now you can see that on the GPU, it takes a fraction, almost a tenth, more than, less than a tenth of the time that it takes on the CPU. That's why, GPU processing is so powerful. And, when possible, you should be using GPUs for training. And sometimes, there are cost issues also. GPUs are also more expensive. So if speed is not an issue, right? If your users can wait, then it makes sense to use the CPU. But if speed is an issue, then it's almost required that you use the GPU. Sometimes you can get away with a CPU and a smaller model, but those are the kinds of design decisions you have to make when you are building an engineering system, right? So lastly, this is the end of this notebook, but for people who want to dig deeper, the people who are really interested to know how the training takes place, how to train a model like this, we only showed you Inference because this is a very short course. We cannot cover everything. But if you're interested in how these models are trained, how, more details about all the different parts, how the architecture is laid out, what were the big ideas in these architectures. If you want to know all the details, and if you are serious about a career in AI and computer vision, then please visit OpenCV University. We have linked here, and you can see there are several courses there that are available. You can take this, deep learning with Pytorch course, or you could take the CVDL master program, which is a collection of all the courses available. So go check this out, opencv.org/university. You can also check out, some of the student testimonials. They have had amazing journeys. They transformed their careers. For example, here, Andy Gillen, he was a mechanical engineering student, and he took our courses. He was able to transform into an AI career. His first job was more than 100K. And soon after that, in about a year or so, he kept working on his skills because he had taken the complete computer vision and deep learning master program. He kept working on his skills, and in 2 years after graduation, he landed a job at Tesla, which pays more than 200K, right? So amazing stories. Check out some of these stories on this page. We have linked to it in this notebook as well. So that's all we have to cover. We wanted to cover in this notebook. We'll in the next notebook, we are going to cover more interesting stuff, including YOLO object detection. That's all we wanted to cover in this notebook. Let's see you in the next notebook. Thank you.